Hi folks. Now that we've learned a little bit about the periodic table and some of the repeating patterns on the periodic table, we're going to look at some of the trends on the periodic table. So just to remind you about these repeating patterns, when elements are arranged in order of increasing atomic number, elements with similar properties appear at regular intervals. Okay. For instance, electron configurations. So we've discussed before how everything in group 1 ends with an S1 in their electron configuration. Valence electrons. We've discussed this pattern of valence electrons. Oxidation states. We've discussed this pattern in common ion charges, and we call those ion charges oxidation states. Reactivity. We are going to learn 4 new trends today, and we're going to need 4 definitions for those 4 trends, and then we'll look at the patterns across the periodic table. So the first new definition that we need to learn is atomic radius, and you should know the word radius from geometry. If you think about the radius of the circle, it's the distance from the center of the circle to the outer edge of the circle. And it's the same thing for the atomic radius. We're measuring from the center of the nucleus to the outside edge of where we think electrons are likely to be, where there's a 90% chance of finding an electron. So radius is half the diameter, just to use another geometry vocab word for you there. Francium, of all the elements on the periodic table, has the largest atomic radius. Now, it may not surprise you that the element with the largest atomic radius is down here at the bottom of the periodic table, but it may surprise you that the largest atomic radius isn't the one with the most protons and neutrons over here on the periodic table. We'll talk about why that is in a moment, but for now, just know that francium has the largest atomic radius. And so the general trend on the periodic table is that the radius increases as you move down the periodic table and to the left on the periodic table. And be sure you add those arrows to your notes and put a star on francium so that you remember who's the biggest. Okay, so why are things on the left of the periodic table larger than things on the right? Okay. Let's look at, we're just going to compare 2 elements that are side by side and discuss those 2 in particular. So we're going to compare sodium and magnesium. Magnesium is smaller than sodium because magnesium has more protons. So it has more positive charge in the nucleus. But it has an equal amount of shielding. And what I mean by shielding is that core electrons are blocking the attraction between the nucleus and the valence electrons. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. 10 electrons shielding the valence shell from the nucleus. And that's true for sodium and for magnesium. They both show 10 electrons in the core, 10 core electrons that are blocking the view of this valence electron from seeing the nucleus, or these valence electrons from seeing the nucleus. So overall, here we have more protons pulling in those electrons. Therefore, magnesium pulls in its outer shell of electrons more tightly, making magnesium smaller. Now, this explanation, if you're one of my CP students, is not something that you have to memorize. If you're an honors student, you do need to know this. But I think it's helpful. It helps you remember the trends better if you understand why it happens. So that is why magnesium is smaller than sodium, because magnesium has more protons and can hold on to those electrons more tightly because they both have the same amount of shielding. So why the atomic radius increases as you move down the periodic table is a little less surprising. It's larger going down the periodic table because the more energy levels you have, the larger the radius is for each subsequent energy level. So higher energy levels are just bigger. They have a larger radius. More shells of electrons means the energy level is getting bigger. You may say, but wait a second, you said that more protons means you hold on to your electrons more tightly. And that's true when the shielding is the same. But in this situation between lithium and sodium, lithium only has 2 electrons shielding the valence shell from the nucleus, whereas sodium has 10 electrons shielding this valence shell from the nucleus. So yes, there are more protons in sodium, but there's also more shielding. There are more electrons kind of blocking the view to the nucleus. So the electrons are not pulled in more tightly with sodium. Okay, so quick practice question. Which one is bigger, beryllium or barium? Find them on your periodic table. Barium. And which one is bigger, calcium or bromine? Calcium. More practice. List the elements, lithium, oxygen, carbon, and fluorine, in order of increasing atomic radius. So when you get a question like this, just make sure you're reading that word carefully and think about what it means. It means smallest to largest. We should have fluorine, then oxygen, then carbon, then lithium. And if you do the same thing for bromine, fluorine, iodine, and chlorine, in order of increasing atomic radius, you should have fluorine, then chlorine, then bromine, then iodine. So I'm not going to go into a lot of detail with the next few trends about the reasoning behind the trend. But the explanation for atomic radius, you can use a similar reasoning for explaining the next few trends. Basically, when you have a small radius, that means valence electrons are held tightly. Therefore, it's hard to lose electrons if you're holding on to that valence shell super tightly. Similarly, it's easy to attract or gain electrons if there's room in the valence shell. It's easy to attract or gain electrons when the radius is small. On the other hand, if you've got a large radius, that means valence electrons are held onto loosely. That means it's going to be easy to lose an electron. It won't take a lot of energy to lose an electron, but it is hard to gain or attract new electrons. So we talked about atomic radius. Now the next trend we're going to talk about is ionization energy. We need a definition for ionization energy first. So ionization energy is the energy required to remove 1 electron from an atom. 1 electron from an atom. And specifically, the first ionization energy is the energy required to remove the first electron. So the most loosely held electron from a neutral atom. So you're starting with neutral and you're creating an ion with a charge of +1. Helium has the very largest first ionization energy. And therefore, you might be able to guess that the trend for ionization energy increases as you move right on the periodic table and up and to the right. And so be sure you add those arrows to your notes and also put a star where helium is so that you remember that it has the highest ionization energy. Why is there more ionization energy as you move to the right? Because there are more protons, but the same amount of shielding. Energies are pulled in more, electrons are pulled in more tightly towards the nucleus and therefore take more energy to remove them. Why does the ionization energy increase as you move down the group? Because higher energy orbitals are further from the nucleus. So there's more shielding, so kind of less attractive force holding them in place. Therefore, electrons are held loosely and easier to remove. Notice that this trend is the opposite direction to atomic radius. So you are going to need to go out of your way to remember the difference in trends. It's because a small radius means valence electrons are close to the nucleus and held tightly. Therefore, electrons are hard to lose. So they have a high ionization energy. It takes a lot of energy to remove them. A large radius means valence electrons are far from the nucleus and held loosely, so electrons are easy to lose. That's low ionization energy. That's why atomic radius has the opposite trend to ionization energy. They are related to each other, but in an opposite direction. Let's practice. Which atom has the higher first ionization energy? Nitrogen or bismuth? It is nitrogen because it's higher up in the periodic table. And how about barium or neon? It is neon because neon is further to the right on the periodic table. Third trend. The third trend we need to learn about is electron affinity. And electron affinity is the energy change when an electron is gained by a neutral atom. When an electron is gained by a neutral atom. Fluorine, out of any element on the periodic table, has the largest electron affinity. We're talking about gaining an electron, so we're talking about making an anion with a negative charge. So you can see from the position of fluorine that the trend is going to increase when we move up the periodic table and to the right, except we do not include the noble gases. The noble gases have extremely low electron affinities, the lowest of on the periodic table, because their valence shell is already full. There's no room for an electron in the valence shell of a noble gas. They would have to start an entirely new energy level, and that is that is not very likely to happen. So be sure to add these arrows to your notes, and be sure to indicate that the noble gases are not included here, and that fluorine is the highest, the element with the highest electron affinity. Why does an electron affinity increase to the right? Because there's more protons but same shielding. So valence electrons are close to the nucleus. When the radius is small, the valence electrons are close to the nucleus, so there's more pull from the nucleus for attracting additional electrons, so long as there's space for an additional electron. They're smaller. Electron affinity is smaller going down a group because these higher energy orbitals are further from the nucleus. There's more shielding, so there's less attractive pull from the nucleus, less ability to attract a whole new electron. So just as a quick practice, which atom has higher electron affinity, sulfur or magnesium? It'll be sulfur because it's further to the right on the periodic table. And aluminum versus gallium? Aluminum because it's higher up the group on the periodic table. The fourth trend we need to know on the periodic table is the trend for electronegativity. And electronegativity is the ability of an atom to attract electrons in a covalent bond, inside of a chemical bond. So we're not talking about making an ion here. On the surface, this sounds a lot like electron affinity, but with electron affinity, we were making an ion. With electronegativity, we're just hogging more than our fair share of electrons inside of a covalent bond. The definition sounded a lot like electron affinity, and the trend is the same as electron affinity. Fluorine has the largest electronegativity. Therefore, the trend is up and to the right, except, again, for those noble gases. Those noble gases have the lowest electronegativity on the periodic table. Their valence shell is already full, so they do not need to bond. Again, add these arrows to your notes. Make note of the fact that fluorine has the highest or the largest electronegativity, and be sure to cross out the noble gases. Why is electronegativity highest as you move to the right? Because there are more protons but the same amount of shielding. Therefore, those valence electrons are close to the nucleus. So it's easier for that nucleus to kind of use its attractive force to attract electrons. So long as there's room in the valence shell, it's easier for that nucleus to attract more electrons towards it. As you move down a group, electronegativity decreases because as you move to higher energy orbitals, those are further from the nucleus, there's more shielding, so there's less pull from the nucleus and less ability to attract an electron. So let's practice. Which atom has the higher electronegativity, polonium or oxygen? Oxygen is further up the group, so it has the higher electronegativity. How about cesium versus lead? Lead has the higher electronegativity because it's further to the right on the periodic table. So I want you to flip back through your notes and summarize the definitions and the trends for these four new definitions that we've learned today. So pause the video and fill in your table. And then you can check your answers and make sure you got everything. You got all the trends correct. Notice that atomic radius is the odd one out in terms of its trend. It decreases as you move left to right across a period. It increases as you move down the periodic table. Everything else has the opposite trend. For first ionization energy, remember that helium is the highest or biggest. But for electron affinity and electronegativity, even though the trends are the same, it's fluorine that is the biggest. So just as some additional practice, you can pause the video and then check your answers. Got beryllium, aluminum, sodium, sulfur, potassium, phosphorus. Again, pause your video and then check your answers. Chlorine, oxygen, lithium, gallium, bromine, oxygen. Try to put these in order. Again, pause the video and give it and then come back and check your answers. And for electronegativity, the trick here with electronegativity is remember that the noble gases have the lowest electronegativity. So you want to put that at the low end and don't try to, even though the trend for increasing electronegativity is up and to the right, and neon is furthest to the right, it has the lowest electronegativity. I hope this helped.